Okay, so question number 8 is basically given a non-empty set X, given a non-empty set X. Consider P of X. Consider P of X, which is basically the power set of X, which means basically all of the subsets of X, meaning that if you have some set X over here which has some elements in it, all of the subsets of X would be basically, for example, if you have these elements in X, like for example A, B, and C, then all of the subsets of X would be, for example, a set containing A, would be a set containing B, would be a set containing C, and then you would have, for example, another set containing A and B. You would have another set containing A and C. You would have another set, for example, containing B and C. You would have another set containing all of them, A, B, and C, meaning the set itself. And you would have the set containing nothing, which is the null set. And you can see that 1, 2, 3, 4, 5, 6, 7, 8 sets you have here. And that's actually 2 raised to the power 3. So the number of elements of X, the number of elements of X, if I call this P, lowercase p, that is equal to 3 here. Now the number of subsets, of X is equal to 2 raised to the power P, which is equal to 2 raised to the power 3, which is equal to 8. And well, if I define the power set of X, the power set of X as basically a set containing all the subsets of X, then the number of elements, and if I denote this by, for example, capital P of X, then the number of elements of P of X would be the same thing, would be basically, well, you would have basically all of these subsets in the power set of X, and therefore that would be again equal to 2 raised to the power P, which is equal to 2 raised to the power 3, which is equal to 8. Which means that in this case, basically P of X would be equal to a set containing all of these sets, containing the set A, the set B, the set C, the set basically A comma B, the set A comma C, the set B comma C, the set containing ABC, and the set containing nothing. That is the power set of X. Now here we are talking about the same thing. So given a non-empty set X, consider P of X, which is the power set of X, which is the set of all of the subsets of X, which is a set of all of the subsets of X, Now define the relation R in P of X as follows. So now that we have understood this part over here, we have a non-empty set X, and consider P of X, which is and consider P of X, which is a set of all of the subsets of X. So we have a non-empty set X, and we are just considering the power set of that non-empty set, which is basically what we talked about here, right? Okay, so the rest of the question is, so let's see what we have here. The rest of the question is, define the relation R in P of X as follows. So you want to define the relation R in P of X, the relation R in P of X as follows. So for subsets A, B in P of X, for subsets A, A and B in P of X, ARB, meaning a relation B, if and only if A is a subset of B. A is a subset of B. Okay. And now is R an equivalence relation on P of X? Is R an equivalence relation on P of X? And justify your answers. So the relation that we have in that we have R in P of X is basically for subsets A and B in P of X. For subsets A and B in P of X, A are B if and only if A is a subset of B, meaning that A is related to B. Such that, for example, you can write this as another way that you can rewrite this notation is that basically here we are saying that ARB is ARB if and only if and only if A is a subset of B, right? So what this means is that, and this is some relation R, that we are talking about. So I can write the relation R as all the subsets A and B, meaning that A comma B, for example, such that A and B, for example, A and B belong to this set P of X. P of X, actually, this is supposed to be capital X, and A is a subset of B. You can write this relation this way if you understand better this way. So now you want to know whether R is an equivalence relation on P of X. In order to basically to find that out, so you know that an equivalence relation is basically a relation that is basically reflexive and symmetric and transitive. Meaning that if you can show that basically R is reflexive, symmetric, and transitive, then that means that R is basically an equivalence relation. So how can we, let's start with the symmetric. So here we are saying that ARB or A is related to B if and only if A is a subset of B. And A and B are basically A and B are these sets in P of X, and X was basically, as we discussed before, is a non-empty set X, and P of X is the power set of X, right? So is the power set of X. Okay. So now the situation that we have here, now A is related to B if and only if A is a subset of B. So let me think about this problem myself and see how we can solve it. Okay, so now in order to show that basically R is reflexive, to check whether basically whether R is reflexive. So you can imagine that reflexive, you can imagine that basically you have these. Let me give you an example so that you can understand this much better. So let's say that you already actually have the example over here. So let's say that you have this set X over here, which contains A, B, and C. Now the set that contains all the subsets of this set X is basically P of X, which is basically all of these sets over here enclosed within another set, which is called P of X, right? Now, what we are saying here is that to check whether R is reflexive, basically the condition that you need to use here is that if A comma A belongs to R, for every A belonging to A, meaning that for every member of the set A, basically A comma A has to belong to R, right? Which means that A has to be related to A for every A belonging to A. Now you can see that in this context, what that means is that every set has to be basically every set that belongs to P of X has to be related to itself. And the condition that we have here is that it says that A is related to B if and only if A is a subset of B. Now since every set is a subset of itself, therefore you can say that A is related to A for all A belonging to P of X, for all A belonging to P of X, right? Meaning that, for example, if you take a look at these sets over here, you of course you know that, for example, this set over here, this set over here, which is, for example, the set A, this is of course a subset of itself. The other set is a subset of itself. The other set is a subset of itself. That means that for every, basically for each and every member of P of X, then you can say that basically generally A comma A belongs to R for every A belonging to A, and so you can say that therefore basically R is reflexive, right? Now, to check whether R is symmetric, symmetric, what we need to check is that we say that for symmetric means that basically we say that if x1 comma x2 belonging to R implies that x2 comma x1 also belongs to R for every x1 and x2 belonging to A, for example, right? Which means that if there is any, for example, in this context, if there is any set that is related to any other set, for example, let's say that you have basically two sets over here, set A and B. Let's say that, for example, there is a set A which is related to the set B. If that is the case, then that has to imply that set B is also related to the set A, meaning that if A is a subset of B, that implies that B is also a subset of A, which is of course not the case. I mean, which cannot be the case ever, because, for example, in a typical example, you can see that, for example, A is a subset of A comma B, right? In this example over here, this set is a subset of this set. So I have this set over here A, and I have another set in the same set, which is A comma B, and I can say that basically this set is a subset of this set over here. We have no problem here, and therefore I can, based on the rule that we have here, I can say that this set is related to this set, right? So we have no problem with that. But the set A comma B is not a subset of this set. Therefore, if I say that, therefore it would be wrong to say that basically the set containing A comma B is related to the set containing A. And so basically you can easily find any sort of counter example like this in order to show that basically R is not symmetric, and therefore basically R is not symmetric. R is not symmetric. Now, to give you a better example here, from the solutions, they say that they have said that let A be related to B, which implies that A is a subset of B. This cannot be implied to B is a subset of A. Well, of course, I mean, most probably what they mean to say is that this does not imply that I would add to this I would add to this, does not imply, or this does not necessarily imply, this does not necessarily imply that basically B is a subset of A. That might be the case, it might not be the case, you simply don't know. And therefore it is not necessary that B is a subset of A, which means that it is not necessary that B is related to A, right? Now, to give you another example here, they have written, for instance, if A is equal to, if A is a set containing 1 and 2, and B is a set containing 1, 2, and 3, right? Then it cannot be implied that B is related to A. Then it cannot be implied that B is related to A. And therefore R is not symmetric. But in this situation, in the exact same situation, if A is a set containing 1 and 2, and B is a set containing 1, 2, and 3, you can say that A is related to B, but you cannot say that basically B is related to A. B is related to A because B is not a subset of A. So you can very easily conclude that R is not symmetric. Now, in order for R to be transitive, in order for R to be transitive, we have basically A comma, or let's say x1, for example. We have x1 comma x2 belonging to R, and x2 comma x3 belonging to R. That must imply that basically x1 comma x3 belongs to R. And of course that for every x1, x2, and x3 belonging to A, right? Now, what that means in this context, in this context that we are talking about, is that suppose that, for example, some set A is related to some set B. So, for example, suppose that some set A is related to some set B, and some set B is related to some set C. That, if that implies that basically A is related to C, then of course for every A, B, and C, if that is the case, of course for every A, B, and C belonging to P of X, then you can say that basically then you can say that R is transitive. Now that can be shown because suppose that, for example, A is related to B. So now if A is related to B, that implies that basically A is a subset of B. And basically B is related to C implies that B is a subset of C. So here we have A is a subset of B, B is a subset of C. From this you can conclude that therefore A is a subset of C. Since A is a subset of C, that implies that A is related to C, which means that basically R is transitive. So what that means is that in simple language, suppose that you have some set A, for example, which is, for example, 1, 2. You have some set B, for example, which is, for example, 1, 2, and 3. You have some set C, for example, which is 1, 2, 3, and 4. Right? So if that is the case, then of course you can say, since A is a subset of B, then you can say that A is related to B. And since B is a subset of C, you can say that B is related to C. Right? And of course you can see that A is a subset of C as well, because A is a subset of B, B is a subset of C, so A is a subset of C automatically. And therefore A is related to C, right? So that is basically, that means that R is transitive. However, R is not an equivalence relation. R is not an equivalence relation since it is not symmetric. Okay. Now that is that. That was question number 8. Question number 9, we have given a non-empty set X. Given a non-empty set X. Given a non-empty set X, consider the binary operation. Consider the binary operation star as a binary operation from the Cartesian product of P of X and and P of X, this is X, and this is the Cartesian product, to P of X given by A star B is equal to A intersection B for all A and B in P of X, where P of X is the power set of X. Where P of X is the power set of X. You want to show that X is the identity element for this operation. You want to show that X is the identity element for this operation, and X is the only invertible element is in P of X, and X is the only invertible element in P of X with respect to the operation star, with respect to the operation star. Right? So the question is, given a non-empty set X, consider the binary operation star, which is basically the binary operation is on the set P of X, which is basically P of X is here the power set of X. So you have the Cartesian product of P of X and P of X, and that goes to basically P of X itself, of course, given by A star B is equal to A intersection B for all A and B in P of X, where P of X is the power set of X. Okay. Now show that X is the identity element for this operation, and for this operation, and X is the only invertible element if in P of X with respect to operation star. Okay, so about this question, first, to understand the question is that given a non-empty set X, consider the binary operation star on the set P of X, and you know that P of X is the power set of X. In the previous example, we talked about about the meaning of the power set of X, so you understand what that means. Now the binary operation is given by A star B is equal to A intersection B for every A and B in P of X, right? Where P of X is the power set of X. Okay, so I suppose you understand the situation. Of course, I'm going to give you an example right now after we're done with this. Show that X is the identity element for this operation. So the first part is that you want to show that X is the identity element for this operation. I'll tell you what this means later once we are solving the problem. And X is the only invertible element in P of X with respect to the operation star. And I'll tell you what this means as well. So now let's start with an example. Let's suppose that you have a set. Let's set the set X as, for example, let's set that the set X is basically a set containing these elements 1, 2, and 3. Now the power set of X is a set that contains all of the subsets of this set, which means that P of X is the same thing as basically the set containing 1, and also the set containing 2, and also the set containing 3, and also the set containing 1, 2, the set containing 1, 3, and the set containing 2, 3, 2, 3, and the set containing 1, 2, 3, and the set containing nothing. And that is the power set of X, which is basically a set containing all of the possible subsets of this set. Now in this set, as you can see, this set here 1, 2, and 3 is exactly the same as X, which is of course the same set X basically, because it's basically a set can be a subset of itself, right? So one of the possible subsets of X is of course itself, and we have written that over here as well. Now what we want to show is that X is the identity element for this operation. So identity element means that the definition for the identity element is that given a basically, if you have a binary operation star on a set A, let's say that you have a binary operation star on a set A, and element E, if you have an element E belonging to A, if it exists, if it exists is called identity for operation star, then E is called the identity for the operation star. If A star E is equal to E star A is equal to E star A is equal to A. That is the meaning of identity. And as you can see here, basically, so you want to show that X is the identity element for this operation. That means that basically you have to show that the intersection of X with any of these elements belonging to P of X is going to be equal to that element, meaning that, for example, if you take the intersection of X with, for example, this set containing 1, that is going to be equal to this set itself. If you take the intersection of the X, which is basically 1, 2, 3, if you take the intersection of that with, for example, this set 1, 2, you are going to get this set again, which is 1, 2, and so on and so forth for all basically let's say for all A belonging to P of X. For all A belonging to P of X, right? And of course that is the case because this is the only set in P of X that if you take it, and if you take the intersection of this set with any of these sets, then you will get the other set that you have chosen to take the intersection of that set with X, of course, and with any other set it's not possible, meaning that, for example, let's take that you take the intersection of this set and this set, you would get the null set. Take the intersection of these two sets, you would get the null set. take the intersection of this set and this set, you would get only basically 3. Take the intersection of, for example, this set and, for example, this set, you would get this set over here. But if you take the intersection of this set with any of these sets, you will get the other set back. Yeah? And that is basically the meaning of the identity set. So what that means is that in order to write this in a better way, I can say that basically we can say that it is given the binary operation, it is given the binary operation star, the binary operation star as a binary operation p of x times p of x to p of x given by a star b is equal to a intersection b for all a and b belonging to, for all basically a and b in p of x. We know that a intersection x is equal to, we know that a intersection with x is equal to x. So here we are saying that basically E is called the identity element for the operation star if A star E is equal to E star A is equal to A, right? So that means that X intersection with A, that is supposed to be A intersection with A, that is supposed to be equal to X intersection with A, and that's supposed to be equal to actually to A, right? That is supposed to be equal to A, of course, not X. So we know that A intersection with X is equal to A is equal to X intersection with A for all A belonging to P of X. For all A belonging to P of X, right? And of course I showed you what that means here, and therefore and that implies that basically then you can write basically A, that is the same thing as A star X, that is the same thing as A star X is the same thing as A is equal to basically X star A for all A belonging to P of X. For all A belonging to P of X. Thus X is the identity element. Thus X is the identity element for the given binary, for the given binary operation star. So the only important thing here to understand is that basically if you have a binary operation star on a set A, basically some element E belonging to A, if it exists, that element E is called the identity, is called the identity for the operation star if A star E is equal to E star A is equal to A for all A belonging to A, of course, right? So if you understand this, then you can generalize it, to any situation, and then basically solve the problem. And for example, in this particular case, so the binary operation is some binary operation on a set P of X, which is the power set of some set X, for example, which is given by A star B is equal to A intersection B for all A and B in P of X. Now we know that basically A intersection X is the same thing as A is equal to X intersection A for all A belonging to P of X, right? And based on what we said here, based on this rule that we had here, so that basically implies that I can write this as A intersection with X. I can write it as A star X is equal to X star A for all A belonging to P of X, and thus X is the identity element for the given binary operation X. For the given binary operation X. Now, the second part of this question is that basically you want to show that X is the only invertible element in P of X with respect to the operation star. X is the only invertible element in P of X with respect to the operation star, right? Now we need a definition here. So the definition that we used here for an element being invertible, we said that given a binary operation star on a set A, meaning that if you have a binary operation star on a set A, with the identity element E in A, E belonging to A, an element A belonging to A is said to be invertible. A belonging to A is said to be invertible with respect to the operation star, if there exists an element B, if there exists B belonging to A such that A star B is equal to B star A is equal to E, and then in this case, if that is the case, then B is called the inverse of A. The inverse of A, and of course A lowercase a we need here. B is called the inverse of A, and A is said to be invertible. Is said to be invertible, right? So what that means is that you have a binary operation star on a set A, and basically the identity that we talked about here, the identity element exists in A, right? So A belonging to A is said to be invertible. Of course, I didn't have to write this over here. So A belonging to A is said to be invertible with respect to star if there exists a B belonging to A such that A star B is equal to B star A is equal to E, the identity element. The identity element here. And B then is called the inverse of A. Now what that means is that you need to find some element, for example A, that if you that if you take the star of that element with some other element b, that binary operation is then equal to b star a, that is equal to e. And e is basically, we found that the identity element for this operation was x, right? So what that means is that, for example, in the case of this example, so x over here is this set containing 1, 2, and 3, right? So the only basically the only element that you can find in here that you can take the star of that element with another element and basically in such a way that a star b is equal to b star a is equal to e, meaning that if you take the intersection of, for example, this set with another set, you will get, you are going to need to get the same set, because here we are saying that a star b is equal to b star a is equal to e, and e in this case is basically the set x itself, right? So what that means is that, for example, if I take any of these elements in here, for example, let's say that I take, for example, this element, the set, for example, 1, 3. Now, if I take the intersection of this set with any of these sets, I'm not going to get this set x over here. And even if I take the intersection of this set with itself, still I'm not going to get the set x over here. The only way that I'm going to get set x over here is that if I take the set x itself, is that I take the set x itself, which is x basically 1, 2, 3, and take the intersection of that with the intersection of x with x, and that gives me x, which I can take basically this as a and take this as b, for example, take the intersection of a and b, and that gives me x. And I can of course write it as b intersection a is also going to be equal to x. And then I can write this situation as a star b is equal to b star a is equal to b star a is equal to x, right? So that the only way that I can get this to this element is basically this way. And this is, and as you can see, this is only possible only if a is equal to b is equal to x. That's the only way that this is possible, right? So now that we have understood this, let's write this down. So you can say that now an element a belonging to P of x, an element a belonging to P of x is invertible, if there exists b belonging to P of x, if there exists b belonging to P of x such that basically a star b is equal to b star a is equal to x, as x is the identity element. As x is the identity element. Otherwise, generally you would write this as for example, generally you would write this as this way, the way that we wrote it here: a star b is equal to b star a is equal to e. Now, since X is the identity element here, we have written this in capital letters because they are referring to sets, and X is the identity element here, which is again a set, right? So so A star B is equal to B star A is equal to X, or you can say that, so an element A belonging to P of X is invertible if there exists B belonging to P of X, such that A star B is equal to B star A is equal to X. Or you can say basically A, for example, based on the rule that we have here, A intersection B is equal to B intersection with A is equal to X. Now this case is possible. This case is possible only when basically A is equal to X is equal to B. So, which means that if you take the intersection of A and B, or if you take the intersection of X and X, you will get X, which is the identity element in here, which means that X is the only the only invertible element in this set P of X. Thus, X is the only invertible element in P of X. Thus, X is the only invertible element in P of X with respect to the given operation star, with respect to star. Hence, the given result is proved. The given result is proved. Okay. Now, this is, of course, these are general situations, and you can, of course, use them in many different types of situations. So, that is basically question number 9. Now, question number 10, we have another question here, number 10. We will do that in the next video. See you in the next video, and thank you.